Hello, in this presentation I will discuss the T confidence intervals. Before discussing confidence intervals, I will have to explain some important concepts. First, I will explain the distinction between parameters and statistics, as well as the concepts of standard error and margin of error. I will explain the use of the T critical value and demonstrate a calculation of the T confidence interval. Finally, I will explain the interconnection between sample size, the standard error, and the margin of error, and the width of the confidence interval. In research and data analysis, it's crucial to understand the distinction between statistics and parameters. Both are numerical values summarizing data, but they differ in terms of the data they describe. Parameters are numerical characteristics of a population. They are fixed values, but in practice they're usually unknown because it is often impractical or impossible to collect data from an entire population. Common examples of parameters include the population mean, the population standard deviation, or the population proportion. For instance, if a researcher wants to know the average score of all high school students in a country on a standardized math test, this average score is a parameter. Since testing every student in the country is impractical, this parameter remains unknown. Statistics are numerical characteristics of a sample, which is a subset of the population. Statistics are used to estimate parameters. They are computed from the sample data and are variable as they can change from one sample to another. Common examples include the sample mean, the sample standard deviation, and the sample proportion. The standard error, noted SE, is a statistical term that measures the accuracy with which a sample represents a population. It quantifies the variability or dispersion of a sample statistic, such as the sample mean, from the true population parameter. The smaller the standard error, the more accurately the sample statistic estimates the population parameter. For the sample mean, x bar, the standard error is calculated as the sample standard deviation divided by the square root of the sample size. Consider, for instance, an educational researcher who wants to estimate the average test score of students in a large school district. The researcher takes a random sample of 50 students and calculates the sample mean test score to be 75, with the sample standard deviation of 10. The standard error of the mean is then calculated by dividing 10 to the square root of 50, and we obtain an approximate value of 1.41. This standard error of 1.41 indicates that the sample mean score of 75 is expected to vary by approximately 1.41 points from the true population mean. The standard error is used to construct confidence intervals around the sample statistic. The standard error is also used in hypothesis testing to determine how far the sample statistic is from the hypothesized population parameter. Additionally, when comparing means between two groups, the standard error helps in determining the significance of the difference between the group means. Understanding the standard error is crucial for accurately interpreting sample data and making inferences about the population, especially in fields like educational research where sample sizes and variability can significantly impact the results. The margin of error, noted ME, is a statistic that expresses the amount of random sampling error in a survey's results, for instance. It defines the range within which the true population parameter is expected to fall, given a certain level of confidence. The margin of error provides an upper and a lower bound around the sample statistic, offering insight into the precision of the estimate. It is a function of the standard error and the desired level of confidence, for instance, 90%, 95%, 98%, and so on. For variables with a normal distribution, the calculation of the margin of error relies on the z-statistic. However, in practice, most variables do not have a perfectly normal distribution, and the margin of error relies on the t-distribution. In practice, the margin of error is most often computed using the t-statistic due to constraints related to sample size and the data distribution. By plugging in the formula for the standard error, the margin of error can be expressed as T star multiplied by the standard error, or T star multiplied by the standard deviation divided by the square root of n, where T star represents the critical value of T for a given confidence level. S is the standard deviation and n is the sample size. The value of T star, or the T critical value, depends on the sample size, or the degrees of freedom, and the desired level of confidence. For manual computations, we obtain this value from the T critical values table. When using software, investigators need to indicate the confidence level, and the value of T star is selected automatically. Investigators may also use online calculators to obtain the value of T star. The value of T star increases as the level of confidence increases. In contrast, T star decreases as the sample size increases. In the table presented on this slide, the columns represent different levels of confidence from 50% to 99.9%, whereas the rows represent different degrees of freedom. In this table, T star for a sample size of 10 and the confidence level of 80% is located at the intersection of the line 9 for 9 degrees of freedom and the column for 80% confidence level. As illustrated here, this value is 1.383. Please note that with the same degrees of freedom, with the same 9 degrees of freedom, but with a 95% confidence interval, the value of T star increases to 2.262. In contrast, for the same confidence level of 80%, but with 10 degrees of freedom, the value of T star decreases to 1.372. For instance, let's say that an educational researcher wants to estimate the average score of students on a standardized test in a large school district. A random sample of 9 students is taken, and the sample mean score is found to be 75 with the sample standard deviation of 9. To calculate the margin of error at a 95% confidence interval, the researcher first calculates the standard error, which is 3. Next, the researcher finds the critical value from the t-distribution table. For 8 degrees of freedom, since df is n minus 1, therefore df is 8. And with the 95% confidence level, the value of T star is 2.306. The margin of error can then be calculated as 2.306 times 3, and we obtain 6.9. This margin of error indicates that the researcher can be 95% confident that the true average test score for the population lies within plus or minus 6.9 points from the sample mean. Understanding the concept of the margin of error is essential for interpreting the reliability and precision of sample estimates, especially in fields such as educational research, where accurate data interpretation is crucial for decision-making and policy development. The margin of error quantifies uncertainty associated with the sample estimate, providing a range within which the true population parameter is likely to fall. It is an integral part of constructing confidence intervals, which are used to estimate population parameters. In survey research, for instance, the margin of error helps interpret the reliability and accuracy of the survey results, indicating how much the sample results can be expected to vary from the true population values. A confidence interval is a range of values derived from the sample statistics that is likely to contain the true population parameter. The confidence level represents the frequency expressed as a percentage with which the interval will contain the population parameter if the same population is sampled multiple times. For example, a 95% confidence interval suggests that if we were to take 100 different samples and compute the confidence interval for each sample, approximately 95 of the 100 confidence intervals will contain the population mean. Confidence intervals can be estimated based on the properties of the distribution. When variables have a perfectly normal distribution, confidence intervals can be calculated using z-scores. However, in practice, most data do not have a normal distribution. Therefore, confidence intervals are most often calculated based on the properties of the t-distribution. For this reason, in this presentation, I will focus on the t-calculation procedure. The t-confidence interval is used to estimate the mean of a normally distributed population, but when the sample size is small, or the population standard deviation is unknown, or the data from the sample have a symmetrical distribution but do not have a perfectly normal distribution. The t-confidence interval for the mean is calculated by adding and subtracting the margin of error from the sample mean. We first calculate the standard error using the standard deviation and the number of observations. Then we calculate the margin of error by multiplying the standard error by the t-critical value. And then we obtain the confidence interval by simply adding and subtracting the margin of error from the sample mean. In practice, we use statistical software to calculate confidence intervals, but it is very helpful to understand the calculation procedure if we want to be able to interpret confidence interval correctly and do it on our own and not rely on others to interpret the numbers for us. For instance, let's imagine that a researcher wants to estimate the average score of a new teaching method's effectiveness on a standardized math test for a small class of students. The researcher takes a random sample of 15 students and records their test scores. The sample mean is 78 and the sample standard deviation is 10. The researcher wants to construct a 95% confidence interval for the population mean score. First, she identifies the degrees of freedom, which is 14, 15 minus 1. Using a t-table or statistical software, the researcher finds the critical t-value for the 95% confidence interval and 14 degrees of freedom, which is approximately 2.145. The confidence interval is then calculated by plugging in these values in the t-confidence interval formula, and we obtain a lower bound of 72.5 and an upper bound of 83.5. Therefore, the 95% confidence interval for the population mean is from 72.5 to 83.5. This interval suggests that the researcher is 95% confident that the true mean score lies between these two values. As indicated in the descriptions and calculations above, there's a strong interconnection between the sample size, the margin of error, and the width of the confidence interval. As sample size increases, the margin of error decreases. This is because the sample size reduces the standard error, which in turn reduces the margin of error. A larger sample size provides more information about the population, leading to a more precise estimate of the population parameter. The margin of error directly determines the width of the confidence interval. Higher confidence levels result in larger critical values, which increase the margin of error and thus widen confidence intervals, whereas a larger sample size increases the reliability of the estimate by reducing the impact of random sampling variation. In this presentation, I explained the distinction between parameters and statistics, as well as the concepts of standard error and margin of error. I explained the use of the t-critical value and demonstrated the calculation of the t-confidence interval. Finally, I discussed the interconnection between sample size, standard error, margin of error, and the width of the confidence interval. I hope that the explanations provided were helpful.